So hi everyone. Today we're talking about again slope. So let's write a couple of things that are related. We're looking at slope. We can also call this instantaneous rate of change. Instantaneous. And this is also called the derivative. Okay, so these three things are synonymous for what we're doing right now. It's the idea of how is the graph changing from one point to another as I'm moving forward. Let's say from left to right. Am I going to be increasing or decreasing? Is the graph increasing or is it decreasing? And in what rate? How fast is it doing it? So I'm going to show you guys a couple of things of what we're doing here. And we'll start with something kind of easy. Well, let's look at a problem that says x squared. F of x, or we call this y is equal to x squared. And what this means is we just look at a parabola. And we could start it off with a line if we really wanted to. But if I say f of x is equal to a line, let's say 3x plus 2, we know what the slope is. The slope is 3, or 3 over 1, 3 over 1. Because as a graph goes forward, 1, 2, put a dot, the slope is 1, 2, 3 over 1. And this slope is the same slope throughout the whole graph. But what happens in the parabola? Because if I pick a point here, that's still going to be 3 over 1. If I pick a point here, it's going to be 3 over 1. No matter what point I pick, it's going to be 3 over 1 because it's changing the same way. It's a straight line, okay? But a parabola here doesn't follow that intuition. It actually changes the way it's rising or increasing, decreasing or increasing. Now, if I show you this parabola here, looking right here, sometimes we're losing value. See, sometimes we're losing, sometimes we're winning. It just depends on where we are on the graph. So it changes, and not only is it negative and positive, it changes how fast it's changing. Like what I mean is, if you look at an upside down parabola, think of a roller coaster. When you're on a roller coaster and then you hit one of those bumps, you're going pretty fast here, but as you reach the top, don't you kind of slow down for a little bit? And then you reach a point where you're floating in space. You're just floating up out of your seat just for a moment before you're being pulled back down due to gravity, okay? So what happens is we're trying to measure how fast you're changing, okay? Now, if we look at the parabola here, I want to make a couple of notes is that we can actually look at a graph and what we call the tangent line. A tangent line is a line that crosses a graph exactly at one point. So if you look, if I ever take a straight line here and I touch a curved surface, you only touch the line at one point. Think of a basketball. If I have a basketball on the floor, how many times does the basketball touch the floor? Well, if you like lie down on the floor, you see it only touches at one small curve. The basketball touches the line at one small point, right? And that's called the tangent line. The tangent line to the curve. And this tangent line is a very nice way to see how much the graph is changing. If I pick another point, let's pick a point up here. You can see that the tangent line by this ruler is actually really steep. And this tangent line is a way for us to visually see that this is a huge change. Now let me go to Desmos here and show you guys this change. Now I've drawn, I'm actually change this to become 0. Okay, so it doesn't give us any problems later. Okay, so we have a graph. You guys can see a point right here at -1. So what happens, what does the slope look like? What does the tangent line look like at that point? And I'm gonna draw a little fake one here. And that's my tangent line. You can see that this is a negative slope. It's decreasing. And you can also see that this graph only touches my x squared graph only at one place. Well, how does this look like when I'm moving it? If I move it around, you can see it changes. As x is bigger, so the tangent line becomes more slopey. It gets, it increases in change. Okay, so it changes, the tangent line kind of follows my curve here. So we're gonna pick an easy example at -1. And I'm gonna ask you guys to just look with me and say, hey, what's the slope of the tangent line? And I can actually count it. We can say the slope of the tangent line is simply put from dot to dot. Okay, these are two easy dots. These are dots right here. We can use any of those dots. -1, -2 over 1. The slope is -2 over 1. And that is how fast this graph is changing, -2 over 1. And that's not too bad. What happens if I pick a different point? If I pick a point that's, let's say, back here at -1, would you guys be okay that this is more slopey, it's more negative? Well, what's the slope here? Since I have the tangent line now, I can actually count it. -1, 2, 3, 4 over 1, -4 over 1. That's even more slopey. And this tangent line tells me a very simple way of us to visualize how fast this line is changing. Am I going to be making money or losing money? Right? If you bought some AMC the other day, AMC has gone up. It doubled in price just today. So let's say we're double in price. We're over here. AMC is right here. We're making money. What would the slope be on this side? Since I have the tangent line already drawn, let's go ahead and count it. The slope is going to be 1, 2 over 1. You guys can see that? Rise 2 over 1. The slope is 2 over 1. And that'd be really nice if I could always just come up with a slope. But in reality, it's not always going to be that nice. If I change my a value here, so it doesn't just go on integers, what if I do 0.5? Okay, so as this goes from 0, negative 0 and over, that's like, what is the slope at x is 0.5? Because I have it drawn out, I can try counting it. And in this case, it's going to be 1 over 1. It's going to be 1 over 1. Okay. Oh, no, it's not 1 over 1, is it? Oh, yeah, it's 1 over 1. Whoops. It is 1 over 1. It's 1 up 1 over 1. See? But it would be harder to find. And so mathematicians had to find a way to say how fast is a line changing or is a graph changing? And because not all lines are straight lines. And they came up with this idea of a derivative. But they didn't just come up with it. They came up with the idea of slope from an algebra standpoint. And they said, fine, how do we talk about slope in algebra 1? Slope is defined by f of b minus f of a over b minus a. And that's how we started talking about this a lesson or two ago. We said slope is f of b over f of a, b minus a. You take your rise in your f's over your run in your x's. And then we said, what if instead of calling this, let's draw you another graph here real quick. We'll use our same parabola. And we'll start at -1 here. Call this a and call some other value b. The problem is to find slope. If this was a straight line, it doesn't matter what 2 points you pick. Any 2 points would give you still the same slope. But when it comes to a line, if I pick a point that's too far away, this line is not representative of the tangent line. It's not what's going on here. It's almost like you have your own story. But I want to talk about my story, but you're talking about your own story. Can you please listen to me? And we realize that as we call that h in this problem. And if h was different, it changed my tangent line, right? It became what we call a secant line. And this is not a good measure of slope because as h got farther, it looks really different than what my actual slope is supposed to be. Now I'm going to go ahead and change this real quick. I'm going to make my tangent line dotted. Let's see if I can do it. It'll let me do it. I'm going to make this a dotted so you guys can see it. That's going to be my tangent line. It's going to be my tangent line forever now, okay? Now, my new line here, that is not a tangent line, but we can make it look like my tangent line. Now, take a look at my h value. If h is really big, it doesn't look right. But if h gets smaller and smaller, as you can see, it's getting smaller. As h gets closer and closer, closer and closer and closer to 0, it's almost like if I want to be best friends with someone and I want to know everything about them, I need to be really close to them to get to know them. And if it's really darn close, the closer it is, the more it looks like my tangent line, till we are actually 0. And we talked about that as a calculus idea. So instead of writing slope this way, we said, what if b was a plus a little bit of h instead? B, this point B is a plus h. And this distance here is h. So we're going to change this equation now. F of B becomes F of A plus H minus F of A over A plus H minus A. Now, please you'll notice something in the bottom. The A's are positive and negative, so these are like terms are going to cancel out. We end up F of A plus H minus F of A over X minus H. So, oops, I don't know what I'm doing. Divide H. So that we're no longer looking at 2 points, we're looking at 1 point. But how far do we want these 2 points to be? Well, H away. Well, do you want H to be a big number or a small number? We said in order to get our slope, we want H to be 0. So the limit as H gets closer to 0 of F of A plus H minus F of A over H. And we're going to rewrite this as a limit as H goes to 0 of F of X plus H minus F of X over H. And this is the way they came up with this idea of finding slope of a curved surface, not a straight line. The curved surface is that they said, I get it. The curved surfaces are constantly changing. Sometimes they're up, sometimes they're down. Sometimes they're really negative, sometimes they're a little bit negative. But we can't use 2 points that are too far away. But what if we made those 2 points right next to each other? And this is what we're going to do now. We're going to use our equation f of x equals to x squared. I want to ask you, what is the slope at x equals to -1? What's the slope at x equals to -1? And we already found that out. We looked at our graph previously and we said, hey, the slope is going to be -2. But I'm going to prove to you that using this limit equation. Now we practiced about doing limits before. Let's go ahead and practice it again. If f of x is equal to x squared, think of this as a jelly donut. You can put whatever filling you want. Do you want raspberry? Do you want strawberry? Do you want blueberry? Do you want custard? Okay. So this is going to change depending on what we want to add into it. So here we go. It's a limit as h goes to 0 of f of x plus h. That means it's the parentheses squared because that's a function. And instead of writing x, I'm going to write a special variable inside, x plus h. I'm going to stick my own jelly filling in it. Minus f of x. Well, isn't f of x just my original x squared equation? And this is f of x plus h. And this is usually where the kids get super confused. They're like, what are you doing? I am just replacing x's for my upgraded version and my original version. Okay, now just to try to get you guys into this, let me finish this all over h. If I wrote f of 3, that's just x squared, so it becomes 3 squared. If I wrote f of 10, that'll be plug in 10 squared. What if I wrote f of z? Well, that becomes z squared. What if I wrote f of r? That's r squared, right? Because it's just the function is x squared, and we substitute whatever we want to plug into it. What if I say fu? F of u? Well, that's u squared. Now, what if I wrote f of x plus h? That's whatever squared, but x plus h is now replaced inside. And that's what we're doing in this front part. And that's, I think, one of the most confusing things for kids seeing this for the first time. They try to overcomplicate it. The idea is whenever you see a variable, instead of plugging x in, you're going to plug x plus h in now. Now, here's what we can try to do. Whenever you have a limit, we could try plugging it in. Now, if I want to plug in our limit, if I plug in 0, h is 0, h is 0, we end up causing a problem. If I plug in 0 right now, I want you guys to all see this. If I plug in 0 right now, it'll be x plus 0 squared minus 0, minus x squared over 0. This becomes x squared minus x squared over 0, which is 0 over 0. What do we say about 0 over 0? Is that an answer that we can take? No, we cannot do this. We want to find another way. So what we're going to do, we're going to go backward, take a step back. And instead of trying to plug in h, we're just going to multiply it out. And this is what you do. You multiply it out. X squared plus 2xh plus h squared minus x squared over h. Seems like I did some crazy stuff, but what is x plus h times x plus h? X plus h times x plus h is x times x is x squared. Bam, done. H plus h is h squared, done. That part's easy. Now what is x plus xh plus xh? Xh plus xh. We end up with two xh's. Square the front, square the back, double the middle. This is our algebra 1 talking. Now, we're kind of doing a lot here, but please realize it's just really just algebra 2 and algebra 1. Now, here's my next step. We practiced before. Get rid of like terms. You always will end up with like terms. Oh man, I forgot to write something. Whenever you do this, you have to write limit because you have to keep writing it. It's almost like your little brother. They're just following you, or little sister. They follow you all around, everywhere around the house, and you can't get rid of them until your parents come home. So we're going to keep the limit there until we plug it in. We're left with the limit. H goes to 0 of 2xh plus h squared all over h. What happened to the x squares? X squared minus x squared cancel out. And this is like the key point right now. If you see, we actually have h's on top and bottom. We can divide out the h's. If I get rid of the h, let me just show you. This is 2x plus h if I factor it out. And you'll notice, if you're paying attention, that you have h's on top and bottom. We rewrite it, limit, as h gets closer to 0. So what does it look like without the h's? Is 2x plus h. Now, what would it look like if h was 0? We can now plug it in, and we end up with 2x plus 0, which is 2x. Now, what does 2x even mean? 2x is the slope. We're talking about, isn't a slope a number? You're right, slope's a number. But this is a slope with a variable because it changes. As x changes, so does my slope. Now, let's do some calculations quickly. If x was -1, right? If x was 0, if x was 1, if x was 2, these are all different parts of the graph. Again, let's look at the graph up here. This is just a parabola. If x was -1, if x was 0, if x was 1, if x was 2, you can see that the tangent line is changing for each of these points. So what would the slope be? Well, our equation for slope is 2x. So all you have to do is plug in the x. 2 times my slope is 2 times -1. My slope at 0 is 2 times 0. My slope at 1 is 2 times 1. My slope at 2 is 2 times 2. So my slope is -2, 0, 2, and 4. So please write that down, and I'm going to show you guys that this is exactly what we just showed a moment ago. We were able to predict what the slopes would be. So let's take a look at the graph. So when a is -1, we can see the tangent line. That's how fast the graph is changing at that very moment. Let's go ahead and count the slope. 1, 2 over 1. -2 over 1, which is -2. If you look at your work and your notes, you'll see that the slope that we predicted at -1 would be -2. What is the slope at 0? When x is 0 here, when x is 0. Here's 0. You can see that it's a flat line. Hopefully you can see a flat line from left to right. That means we made no money today. That would be a slope of 0, which is what we predicted. What is the slope at 1? The slope at 1 is 1, 2 over 1. Hey, that's a slope, 2 over 1. That's what we predicted. What's the slope at 2? Now this one's going to be a little weird. I'm going to count the other way, but this is going to be from, let's do from here. 1, 2, 3, 4 over 1. 4 over 1, which is 4, which is the slope that we have predicted. What happens is we didn't just talk about one slope. We found all the slopes in the whole problem. Every time you give an x, I can tell you what the predicted value for that slope is. That's crazy. Yeah, it is. What are you talking about, Ms. Go? I'm so confused. Our idea here is that instead of graphing our graph over and over again, so we just predicted all our slopes for x squared. Now, how does this work for other problems? Well, let me give you another problem. If I say y is equal to 2x plus 1, okay? Y is equal to 2x, so let's do 2x squared, okay? 2x squared plus 1. Now, this graph is a little bit different, okay? So if I'm asking for the slope, well, remember this is f of x also, right? Fine, let's find the slope equation. The slope equation is f of x plus h minus f of x all over h, and as a limit of h goes to 0, meaning how far are the h's away from each other? Or the 2 points are practically 0. They're right on top of each other. Because if I make h too large, we don't get a good tangent line. So here's what we do. We say, hey, what is the function? The function here is 2x squared plus 1. So in the front, I'm going to plug in, please be aware, remember, I'm going to plug in x plus h. So in this problem, it's going to be the limit as h gets closer to 0 of 2 blank plus 1 minus 2x squared plus 1 all over h. Now, please take a look. It's the new version. It's my new iPhone 12, whatever it is, versus my old iPhone 8. So we just copy this back here. Why? Because that's just f of x. The front changes. It's still 2x squared plus 1, but x is now written in a new way with the upgraded x plus h. When you guys take this in calculus, that's all you do with this problem. You write the new version in front and the old version in back. The new minus the old gives you the difference. Okay, so here we go. We're going to multiply this out. This is going to be 2 times x squared plus 2xh plus h squared. Okay, that's what we're going to do. We're going to multiply the 2. I just wrote there so you guys can see it. This is the x squared. Okay, the limit as h gets closer to 0 of 2 times x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1 all over h. Now, this looks like it's a lot of work, but honestly, it's just me copying it. Oh, I forgot to correct plus 1. I'm sorry. Can you see any like terms on top with 2x squared? Do you see another 2x squared on top? They cancel out. How about the 1? Anyone who doesn't have an h is going to get canceled out if you did this correctly. Anyone who doesn't have an h, we're going to rewrite this one more time. The limit, h gets closer to 0 of 4xh plus 2h squared over h. Look at this problem now. We have h's everywhere that we can divide out. Perfect. The limit, as h gets closer to 0 of 4x plus 2h. We're almost done. We can plug in the 0. Our slope is 4x. Now this is a slope for the whole graph. For the whole graph. Now, is this going to be true? Let's give us a value. If x is equal to 1, what will the slope be? If x is equal to 2, what is the slope be? What if x was equal to -1, what would the slope be? And we make predictions. The slope would be 4 times 1, because x is 1. The second one, 4 times 2, because x is 2. And the slope at -1 would be 4 times -1. So it would be -4. It's going to be 8, and this is going to be 4. So I'm going to show you this real quick on our Desmos graph. We're going to change it to 2x squared plus 4, right? Change that to 2x squared plus 4. Oh, I deleted it already, darn it. 2x squared plus 4. Okay. We're going to be at -1. Sorry, I deleted it, so I have to rechange it. Okay, here we go. So here's my graph. At -1, my slope is going to be, I want to give myself a small edge here. And this is an easy way for us to look at it. Okay. No, too much. So I'm trying to get the h to be as small as possible. No, that's good enough. Okay, so we claimed in our last problem that the slope would be 4. Oh, sorry, let's look at -1 for instance, we're there. And -1 would be -4, okay? -4. Let's see if the slope is -4. -1, 2, 3, 4/1. Yep, that slope is -4. What about the slope at +1? Okay, +1. What does the slope look like? Let's go here. The 1, 2, 3, 4/1. See, that's the slope of this line. The tangent line, the slope is +4/1. That means that's how fast the line is changing at that very moment. The tangent line represents how fast the line is changing. And then if the x was 2, let's go make x goes to 2. Now this line is going to be harder to count. It looks kind of steep, but let's see if we can hit it. I see 2 points that are pretty easy to use. We'll use this point down here and this point up here. Our goal is to get to 8. 1, 2, 3, 4, 5, 6, 7, 8/1. That's some pretty crazy growth there, 8/1, and that's what we have. So we're able to predict it. Now, I just want to introduce you guys one more thing today. I know I'm running out of time, but it's about square roots. And I want to show you that this works for pretty much every type of function that we've learned already, sine, cosine, tangent. We can find the derivative of it. Takes a little more work for those, the trig ones, but anything with a fraction or a square root, we can actually do. Let's do y is equal to f of x equals to the square root of x. Now, I'm going to show you this demonstration of how this one is done. You might freak out a little bit, but it's really just algebra 2, and you've actually learned how to do this method already. So the limit as h gets closer to 0 of f of x plus h minus f of x over h is the limit as h gets closer to 0 of, plug it in, the square root of the new minus the square root of the old. The new value will be x plus h. Whenever you see an x, you're just going to replace that with the new version, x plus h. Now, we could plug in 0 here and you'll get the same thing. You end up with 0/0. And we don't want to do that. Now, how am I supposed to simplify this problem? And it's going to be a tool that we learned from before. And in this case, how to get rid of the square roots? It's what we call the conjugate. So we're going to multiply this by the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. And this was one way for us to rewrite the problem. And this is a hint. For each of these problems in calculus, you have to know what is the gimmick. What is the gimmick? When you talk to your mom, you talk to her a certain way if you want something. You talk to your dad, you talk to him in a different way. Everyone has their gimmicks. You talk to your teachers a certain way. So here's what we do. If I multiply this out, it's going to be automatically a simple trick. Limit as h gets closer to 0 of square root times the square root times the square root goes away, and we're left with x plus h. If I multiply these together, 1 and 2, you'll see that these are actually twins. There's a good twin and there's a bad twin. They should cancel each other out. So we don't even worry about them. Minus x, because the square root of x and square root of x is just x. All over h times the square root of x plus h plus the square root of x. In this problem, we do not multiply out the bottom. But please look at the top. You notice something cancels out on the top. The limit as h gets closer to 0 of the x's, see you later, because x minus x is 0, h over h. Remember how we said we have that h over h problem? And it just revealed itself. It wasn't natural before. We didn't see it, but then it revealed itself. It just go away. Now we have sorry, the limit as h gets closer to 0, 1 over square root of x plus h plus square root of x. Now, here's our last step here. We're going to plug in the 0. Take a look here, plug in the 0, because we want those 2 points to be 0 spaces apart. And now when we plug in the 0, we have no problem. We're not going to be divided by 0 anymore. 1 over 2 square root of x. Now, here is my crazy part. I'm telling you that this slope is the slope for the whole graph of square root of x. You might not even remember what square root of x is, like what the graph is, but it is a sideways parabola going this way. That's square root of x graph. So at x is equal to 1, what is the slope? We'll plug it in. 1 over 2 times x is 1. 1 over 2 times 1 is 1 over 2. My bet is that when x is 1, my slope is going to be 2 over 1. So 1 over 2, 1 over 2. That is my bet for you. Let's go and take a look at the graph. If I change the graph to become square root of x to the 1/2 power, oops, didn't work out. 1/2 power. Okay, that's my graph. If you guys take a look, that is my graph here. And we have our tangent line that's really close. I used 0.06. Now let's take a look at if my slope is really 1 over 2. We're going to change it to 1 right here. Okay, here we go. My slope, is it 1 over 2? Looking at this red line, okay, we're looking at this red line here. That's the line we're trying to find the slope of. 1 over 2. That's exactly what we were hoping for. If I want the slope at 2, right? Sorry, we can do it at 4. 4 is easy, right? Square root of 4 is 2. We would figure out that is 1 over 4, I think. If I use x is equal to 4, 1 over 2 square root of 4 is 1 over 2 times 2 is 1 over 4. Okay, so my bet is that at x equals to 4, my slope is 1 over 4. So let's move it to 4 real quick. You guys see the 4? And then I can count for you guys. Take a look at the slope. I can tell you it's going at 1, 1, 2, 3, 4. That is the rate of change. And that's represented by the tangent line. Okay. All right. So your IXL, you guys will be practicing this. This is pretty much it for the class. We ran out of time. But yeah, thanks.